design of 3-bit up counters in the last lecture. So we stopped until the formation of K maps in the case of synchronous 3-bit up counters. So the next step, as I told you earlier, is drawing the circuit diagram. So this was the K maps formed. We formed the equation for J3. Please see the cursor movement. We formed the equation of J3 as Q2 Q1, K3 as Q2 Q1, J2 and K2 as Q1. Now, how can you draw the circuit? This is how you can draw the circuit. You know that it is a 3-bit counter. So you need 3 flip-flops. One flip-flop is this, second flip-flop is this, third flip-flop is this. Now you know that J1 and K1 are 1. Please see the cursor movement. J1 and K1 are 1. So connect it to 1. Now you know that J2 and K2 is equal to Q1. So you bring a connection from Q1 to J2 and to K2. Now Q1 into Q2. It will be through an AND gate. You take Q2, Q1 and provide to J3 as well as K3. This is how you draw the logic diagram. And please don't forget to draw the clock parallelly to all the flip-flops. So this is how you draw the logic circuit. Now, since until this is over, now we'll go to the design of n-bit down counters. So, in the design of any counter, what is the first step? The first step, see here, the first step is determining the number of flip-flops required. So, we require 3 flip-flops since it is 3-bit counter. Now, what is the next step? Drawing the state diagram. It is a down counter. So, initially all the flip-flops will be reset. So, always, even if it is a down counter, the starting state will be 0, 0, 0. But, since it is a down counter, from the initial position, it goes directly to 1, 1, 1. See here. 1, 1, 1, then it counts down 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. So initially the state will be 0, 0, 0, then it directly goes to 1, 1, 1 state and then counts down. So how can you draw the state diagram? You start from 0, 0, 0, then the next state will be 1, 1, 1, then the next state will be 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. Again, it repeats. Now, what is the third step? Selecting the type of flip-flop. Here also you have selected JK flip-flop, and please keep in mind this is the excitation table of a single JK flip-flop. You write the QN plus 1 combinations and JK. You please learn it by heart. So you know that when your QN plus 1 combination, that is present state QN, next state QN, 0, 0, J and K are 0x. When QN plus 1 is 0, 1, it is 1x. 1, 0, x1. 1, 1, x0. Please keep this in mind. You can form now, the next step is counters excitation table. It has present state, next state and required excitation. So present state, you have to write all the present states that the counter passes. So this is the first thing you have to write. How will you write the present state? You know that the first state is 0, 0, 0. See here, 0, 0, 0. Then it goes to 1, 1, 1. It counts down 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. So, now you have to write the next state. If your present state is 0, 0, 0, what is the next state? It will be counting 1, 1, 1. If your present state is 1, 1, 1, what is the next state? 1, 1, 0, 1 count down. If your present state is 1, 1, 0, it is 1, 0, 1. You have to write it this way. Now, after writing the next state, you can write the desired excitation. How can you write the desired excitation? Using Q3 and Q3. Q3 in present state, Q3 in next state, you can write J3 and K3. Similarly, using Q2 and Q2. Q2 in present state, Q2 in next state, you can write J2 and K2. Similarly, using Q1 in present state, Q1 in next state, you can write J1 and K1. For example, Q3 in present state 0, 1. So Qn plus 1 combination for third flip-flop is 0, 1. How can you write? If it is 0, 1, it will be 1x. If it is 1, 1, it will be x0. If Q3 is 1, here the Q3 is 1, the correspondingly J3, K3 will be x0. Similarly, you can complete the entire table. So first you write the present states, then for each of the present state, write the next state, complete the next states table, then you find the required excitation. So what is the fourth step? Obtaining the minimal expressions. So what you do is go back using this, form the K-map. So in the K-map, if 0, 0, 0 is coming, put 1. First take the case of J3 alone. Form the equation for J3 alone. So this is your input side and this is the output side. Form the K-map for J3. Similarly, take all these, form the K-map for K3. Similarly, obtain the equation for J2, K2, J1 and K1. So in the K-map for J3, look here, corresponding to 0, 0, 0, it is 1. 1, 1, 1, x. See the next one. For J3, 0, 0, 0, it is 1. 1, 1, 1, it is x. Similarly, fill all the others, group it as pair and write the equation. Similarly, do it for K3, J2, K2. This is what we have to do. Now, here also, there's no need to find the K-map for J1 and K1 because even if you form the K-map, all the components inside the K-map will be 1 and x. So, the grouping will be full. The full object will be chosen and you can write J1 as 1 and K1 as 1. That is why you don't need to just draw it for J1 and K1. Now, what is the last step? Drawing the circuit diagram. So here you can see it, J3 and K3 are Q2 complement, Q1 complement. J2 is Q1 complement. You can draw the circuit with that. You draw 3 flip-flops. J1 and K1 are 1. It is connected to 1. Now, Q1 complement will be connected to J2 and K2. Similarly, Q1 complement and Q2 complement will be ANDed and given to J3 and K3. Don't forget to give the clock parallelly to all the flip-flops. So, what I have to say you all is that please memorize the steps in design of a synchronous 3-bit up or down counter. For any counter design, the first step will be deciding the number of flip-flops. Then you have to decide the state transition diagram. Then you have to decide the type of flip-flop and then form the excitation table of the counter. Then form the equations for the inputs. Then draw the logic diagram. These steps have to be followed for any counter design. Okay, thank you.